We begin by considering the force, F12, that is exerted on the positive charge Q2 by the positive charge Q1 as shown. We know that we can calculate this force from Coulomb's law. The magnitude of the force is proportional to the product of the charges, Q1 times Q2, and is inversely proportional to the square of the distance between them, r squared. Since these are both positive charges, the force is repulsive, and F12 points away from Q1 as shown. Suppose now we double the magnitude of the charge Q2, keeping everything else constant. How will the force on Q2 change? Since F12 is proportional to Q2, the magnitude of F12 will simply double, and its direction will remain the same. Something is staying constant here, and that something is the force on Q2 divided by the magnitude of Q2. This constant, the force per unit charge, is really identified with the position of Q2. This force per unit charge at the position of Q2 is totally determined by the magnitude and location of Q1. We will call this quantity the electric field. It is important to note, however, that the electric field is a much more significant quantity than you might guess from this simple definition. Later we will learn that the electric field is in fact quite real, and not just a mathematical convenience. In particular, energy is stored in the field, and information about changes in the charge distribution is transmitted through space via the field at a finite speed, namely the speed of light. We will spend the rest of this pre-lecture determining the form of the electric fields that are produced by both discrete and continuous static charge distributions.